Welcome again to lecture number 10. End of the first week, we are going to review all of what we've covered so far this semester. So chapter 1, picturing distributions with graphs. So let's go through what we did. We defined, of course, statistics. What statistics is, it's a science, it's a branch of mathematics. In statistics, we talk about the individuals under consideration and their various characteristics, which we call the variables. We saw that variables come in multiple types, but it looks like we haven't gotten to that yet, so we will soon. Right? Okay. Here we go, the types of variables. So there's categorical variables. Categorical variables is when you place the individuals into categories, blue eyes, brown eyes, and so on. It's a category, not a quantitative measure. But height and weight would be quantitative. They take numerical values for which arithmetic operations make sense. What are some numerical values for which arithmetic operations do not make sense? That would be something like zip codes, which is an example that we've used before. They are, they don't make sense. You can't average zip codes. So just because things are numbers does not make them quantitative, but the ones that are quantitative are things that you can, that when you do math in them, they do make sense, and they usually come with a unit of measurements. So dollars, inches, pounds, etc. We don't gotta do the questions. We don't gotta do these. So exploratory data analysis is the process of using statistical tools and ideas to examine data in order to describe their main features, right? Exploratory data analysis, okay? We talked about the distribution of a variable. Now, if it's a basically, I mean, we later in the course, we talked about density curves, and we talk about distributions of variables in a more sophisticated context. But this one is simply what are all the values that the variable can take and how often does it take those values. That's the definition that we use when we actually have a sample. Because if we actually have a sample, then I can tell you this one occurred 19 times, this one occurred 22 times, this one occurred 117 times, and so on. Later for density curves, it's more about a theoretical. If you have a situation which is described by this density curve, what percentage would fall into each region, that is a different type. We'll get to there later. In terms of categorical variables, it's very similar. You list the categories, and then you say how many fell in each category, or maybe what percent fell in each category. Okay, so question. How do we describe categorical data? We did this last quiz as one of the questions. There's two ways of describing categorical data, either using a pie chart or a bar graph. So there's pictures here, right? A pie chart, you list all the different categories, and the area of each of the wedges is indicative of the percentage of the total area. So this is like 20, no, let's see, it's 50, 25, this is like 13, 14%. Let's see, orange, biological, yeah, 14.9%, and so on. If you add up the percents, they might not add to 100 because you could always have some rounding error. These numbers are all rounded. And when you add up a bunch of rounded errors, you're not necessarily going to get 100%, even though, you know, in reality, if you kept all those decimals, you would. Then we have pie charts. Well, sorry, we did pie charts, but now we have bar graphs. A bar graph is exactly the same thing, is exactly the same information. What's the difference? The difference is that here you're listing the categories using bars instead of wedges of the pie, where the heights correspond to the frequencies or possibly to the proportions. So in this case, for example, you see arts and humanities is up here at around 10 because it's 10.1% of the students study arts and humanities, not 10.1 or 10 students. There's 1.5 million of them, but these are already listed as percents. But if I want to do the actual numbers, I can do that too. It's just, of course, my scale will be very different. Question, 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 question. Now we have quantitative data. Quantitative data came in two types, or at least was described in two ways, using a histogram, which looks very much like a bar graph. The difference is that there's no gaps. I don't see a picture here, but as we'll see in a minute, there's no gaps in the data. And then a stem plot, which is in one way better than a histogram, because what does a stem plot have that a histogram does not?
The specific numbers instead of ranges for histogram.
Excellent. Right? The stem plot has the specific numbers. I don't lose that information like I would for a histogram. But again, even for a stem plot, there is no gap. So there's a few times that a histogram would be appropriate, more so than a stem plot. Of course, there's lots and lots and lots and lots of values. Writing out a stem plot is just really not realistic. So in that case, I would certainly want to use a histogram. I try to make the classes equal widths, but even for that situation, just so you know, there's many times that you just say, and the rest, once you get to a certain point, so that last one is wider. You count how many fall into each interval, or what percent fell into each interval. You got to make sure the end point of the left and right is consistent with which one it's going to be. And you want the bar heights to be proportional to the number of observations, or the percent. So if something is twice as much, it should be twice as high, so that visually we can interpret it correctly. Here there's a bar for each one. There's no gaps, but in theory there could be. All right, and what are the things that we look for? We look for the overall pattern in terms of whether it's symmetric, right skewed, or left skewed. Are there any deviations or outliers? What is the, I guess the pattern includes shape, center, and variability. Where's the middle? How spread out is it? And are there any outliers? So those are the big things for histograms. We talked about that. We have a question, we have an answer, we have another question, we have another question, and 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 an answer, and a question, and a question, another question. And then we had stem and leaf plots, which we talked about. Stem and leaf plots, you write all of your data. The last digit is the leaf, and all digits that come before it are your stems. So a stem of 19, 15, 13, 11, 12, and so on. This one here, 128, I would put an 8 by the stem of 112. I can't move this, it's a little off. No gaps. So even if something does not appear, if there's no 11 somethings, I would still put the 11 here. I would just leave this blank. Usually, if there's not a lot of stems, you can split stems, do a split stem and leaf plot, like 15 is twice, 16 is twice, 17 is twice, 0 to 4 or 5 to 9, 0 to 4 or 5 to 9, and so on. You can always do that. These are all things that we've seen before, correct? Nothing new here. Question, 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 question. And then we had a special case of a time plot. A time plot's not really the same type of situation as the rest. A time plot's when you look at one specific type of variable and you do it over and over and over again at various points in time. And you're looking for the overall trends. You're looking for seasonal variations. Does it keep going up and down like every summer, every winter, stuff like that? Are there any overall patterns to it? Are there deviations from that? And we usually connect them by data lines, not by curves. So you don't try to fit the curve to it, but rather it's straight lines that connect them from point to point. You can compare it easily here. Private seems to increase more rapidly than public, which is fairly constant over time. Question, question, answer, question, 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 question. And that's the end of PowerPoint number 1. So are there any questions on PowerPoint number 1? Okay, well, good times. Let's go now to PowerPoint number 2. How do I exit out of this?
Does the time plot
What?
go under quantitative?
Say that again?
Does the time plot go under quantitative?
Yeah, I guess because you can't really, I mean, if there are categories, if things change from one, how would something change over time from one category to another? And even if they did, would you say it went up? Would you say it went down? It doesn't seem like it's a valid way of thinking about it. So in that case, yeah, I would say 100% it's a quantitative variable. Make sense?
Yes.
Okay. How do I X out of here? Unless I can go directly to the next one. I can. Crazy. Okay, found it. All right, let's go back to sharing. Okay, so now we are number 2, describing distributions with numbers. So last chapter was very qualitative, not numerical. So describing distributions with numbers makes things much more rigorous. So let's see what we do here. We first define the mean. The mean is the sum of all of your observations divided by how many there are. Of course, this only makes sense for quantitative data. We described it by X bar. That's the sample mean. And then we had a question on it, and then another question on it. And then we had the median. The median is the midpoint. You put all your data from lowest to highest, and it's the one in the middle. And we talked a little bit about what happens if it's an odd number versus if it's an even number, and that is easily fixed by the n+1/2 rule, which says either way, whether it's odd or even, you see how many observations you have, you add 1, you divide by 2. And that observation is the median. So if there's 10 observations, 10 plus 1/2 is 5.5. It is a 5.5th observation. What does that mean, the 5.5th observation? Halfway between the 5th and the 6th observation. If it's n is odd, of course, like 11, it's even easier. 11 plus 1/2 is 6. It's just a 6th observation. Not the median is 6, but it's in the 6th spot. Does that make sense? I hope so. This is all review. This is not teaching for the first time. So a stem plot, of course, makes it kind of easy to see what the median is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 plus 1 is 16. Over 2 is 8. So it's a 1, 2, 3, 4, 5, 6, 7, 8. There it is. 20 is the median. Questions. Mean versus the median. Why would I choose one versus the other? Who can tell me when I would use the mean and when I would use the median?
When everything is symmetrical mean, or when there's a significant outlier, you use median because of the resistance.
Good. So use mean when skewed. Right. Oh, wait. Use median when skewed. Sorry. Yes. So use the mean if it's symmetric and there's no outliers, because outliers can drastically affect the mean because it's a non-resistant measure. And you use the median when it's skewed because the median is a resistant measure. Right? So then we had examples here, the mean, the median, the mode all in the right place. Mode being the highest point. Here the mode's still the highest point, but because it's right skewed, the mean is pulled far to the right, more so than the median, because the mean is non-resistant and the median is resistant. Doesn't mean it won't move at all, it just means it won't move as much. Left skewed, very similar. Mode is the peak, median is pulled a little, mean pulled a lot. Here, the U-shaped distribution, the mode, there's bimodal, there's 2 different modes, but because it's symmetric, the mean and the median are both in the same place. Okay. Question. All right, so then we have the concept of variability, because we have to remind ourselves that if we just talk about the center, it can be very misleading because 2 different graphs can have the same center, but be drastically different in terms of their spread. So how do we affect that? So the first thing we do is we want a measure of spread, how spread out they are. The easiest is just the range, biggest minus smallest. But even that's not the greatest because biggest minus smallest doesn't take into account whether there's lots of things on the sides or in the middle. And by the way, on the quiz, which we should probably also go over today before, in fact, you know what? Well, I'll wait. Before the test, we should go over the answers to the quiz. No, I'm okay. One of the questions in the quiz was you had two different distributions. One of them was kind of normal looking, and one of them was more U-shaped looking, and the answer was which one had the smaller standard deviation. Although, yeah, I'll do that now anyways. So which one had the smaller standard deviation? So the answer was the normal one did. Quiz 1, we didn't. Oh, that's right. I'm thinking of a different class. All right. I'm thinking of a different class. I need more sleep. Never mind. I'm thinking of a different class. So, sorry. So never mind. So measures of spread. So with the measure of spread, if you just look at the largest and the smallest, it's not enough because maybe they're outliers. I don't know. Yeah, I need a nap. Maybe they're outliers. I don't know. But you just have one big, one small. But what's happening in between? There can be many different situations with the same biggest and smallest with things happening in between. So to that end, we come up with a thing called the IQR, the interquartile range. But to do that, we first have to find the quartiles. How do we find them? Take the median and take the median of the left side and the median of the right side. The median of the left side, we're calling that Q1, the first quartile. Median of the right side, that's Q3, that's the third quartile. And each quartile breaks up the data into roughly 25%. 25% from lowest to the first quartile, 25% from first quartile to the median, 25% from the median to the third quartile, and 25% from the third quartile to the maximum. And the interquartile range is a better measure of spread because the outliers and the wings are not necessarily as important as the center 50%. Okay, so the 5-number summary are just those 5 numbers. Those 5 numbers alone, the minimum, the first quartile, the median, the third quartile, the maximum, and give a very encompassing summary of the data. And we create this thing called a box plot, which we'll get to in a minute, to visualize it. For now, we could also use the IQR, which is just Q3 minus Q1, to come up with a mathematical test for whether or not something is an outlier. You take the IQR, you multiply it by 1.5, and when you do that, you go Q3 to the right by that much and Q1 to the left by that much, and any data points past that are considered outliers. So examples, we did these questions, box plots, of course, we talked about the box plot, which is the minimum, Q1, median, Q3, maximum. Are we going to have questions where we need algebra to find the missing variable in an equation? I would have to say that you're not going to have any questions that are not representative by what you've done either in class or on homework. So if you haven't seen any question like that or a situation, you should be okay. Okay. Anyways, so here we have a modified box plot. Remember, a modified box plot, once you've decided that something is an outlier, then rather than having the whisker, it's called stem and whisker, box plots are also called box and whisker plots. The whisker does not go all the way there. It stops at the previous value, and you just put a star there. Of course, if there's no outliers, it's just a good old-fashioned box and whisker plot. And they can be vertical or horizontal. Question. Okay, so the box plots are associated with what the graph looks like. Notice that if the piece is longer, then it's stretched out. So here, this is the smallest part, which means it's not going to be as wide from the right side of the peak to the left side of the peak. But as it comes down, it really stretches out. So you have a big left skewed distribution and not so much on the right. You can kind of try to make your graph. Well, let's start with the bell shape. Maybe that'll be easier. So each of these sections, this section here, 1, 2, 3, and 4 is roughly 25% of the data. So if you go from the center, which is the median or mean for a bell-shaped curve, to the right 25%, to the left 25%. This is not one deviation, by the way, because if you recall, one deviation is how much percent? What percent is one deviation to the right or left?
68.
About 68%. So that's 34% each, and not 25, but it's pretty close. But nevertheless, these are short, these are longer, which means they're going to be spread out over there. Short, a little longer, much longer, which means it's going to be lengthier on that side. Opposite here. Regular size, a little shorter, regular size, really long, so it's long there. Here we have, these are symmetric but long, so it's going to be wide and shallow. And these are small, so it's going to be thin and high. And here they're all exactly the same size, so the height is exactly the same. Uniform distribution. Question. 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 He's going forever. Then we have standard deviation. Standard deviation had its own formula, a little more complicated, but from a mathematical standpoint, better than the IQR. There's a method of, get the mean, get the deviations, square them, add them, divide by n-1, take the square root, the whole thing. We talked about that. Some questions. Using technology, some properties of S. So n-1, what you divide by is called the number of degrees of freedom. It measures the variability about the mean and should only be used with the mean. I've stressed that the first time through. Standard deviation goes with the mean and median goes with the IQR. They do not overlap. Like the mean X bar, S is not resistant. A few outliers, it can change it considerably. S is never negative because you're squaring things, adding them, square rooting. So you're never going to have negative, but it could be 0 if every value is exactly the same. The more variable, S gets larger. Makes sense. S has the same units as the original. So if you're measuring something in feet, the standard deviation will also be in feet. And that's why we prefer it to the variance, which is a square of the standard deviation, because the variance would be in feet squared. And we prefer having the same units. Question. Right, so how do you pick? We talked about that. Mean goes with the SDDev, and median goes with the IQR. Median for skewed and outliers, mean for symmetric and not outliers. Question. And we're done with that one. Any questions on that PowerPoint? All right, chapter 3, the normal distribution. So a density curve is an approximation to a histogram, where you kind of smooth it out. And you imagine that rather than having a small sample, you have an infinitely large sample. So the proportions are as accurate as possible. And most of the time you'll have situations like, oh, this is approximately normal, or this can be modeled by a normal, even though in reality, nothing is really actually normal, but it can be modeled that way. And it's gonna have the shape, center, variability, the same overall patterns that we're looking for in histograms. Is it right skewed, left skewed, symmetric, uniform, U-shaped, all the different possibilities. So the density curve has to be have an area under it of 1, because the total area under it is 100%. It has to represent every possible outcome. And of course, it cannot go negative, because how do you have a negative probability? Those are the two conditions to be a valid density curve. Just because you're a valid density curve does not mean you're applicable to a situation. Different density curves apply to different situations. But here are the keys: always on or above the x-axis and has an area of 1. Okay, it describes the overall pattern. Okay, no set of real data is exactly described by a density curve. Okay, it's not exactly a density curve, but it's close enough for you to do actual calculations with. The median of the density curve is 50% left, 50% right. So if it's symmetric, the median is going to be right in the middle. If it's skewed one way, then the median is pulled along for the ride, just not as much as the mean. The mean is the balance point. If you imagine this being a physical object, and you have a little, tripod, pivot, whatever they're called.
Fulcrum.
What is it? Fulcrum? That's the word, fulcrum. And you balance the distribution right at the fulcrum. The mean is the location where it'll be perfectly balanced. So if it's pulled to the right, then the mean has to be moved more to the right for perfect balance. The median is still 50% left, 50% right, but the mean and median are different, okay? Mode, of course, is just the peak, so that doesn't change. When we talk about density curves, we have two different scenarios. We have actual observations, and then we have the theoretical values. So the actual observations come from a sample. We use X bar and S for the sample mean and the sample standard deviation. But if I can somehow know the actual density curve and the real situation that applies for the entire thing, I would use mu and sigma, the Greek letters, for the population mean and the population standard deviation, okay? And out of all density curves, normal is the most important. It's symmetric, single peaked, bell-shaped, and mu is the center, and sigma goes from the center to the point, what's called the inflection point, where the graph changes from being kind of like a hill and becomes more, it becomes more like a bowl. If you give me mu and sigma, you have completely described the normal curve. Every two normal curves in existence that have the same mu and sigma are the same. You change one of them, it's a different normal curve, okay? But they only require two things to completely specify: mu and sigma. It's kind of like being able to specify every person in the planet by who their parents are and what number child they are from those parents. You tell me who the parents are and which number child you are, you've uniquely determines the person in question. So here too, you tell me, first of all, that it's normal, what the mean is, and what the deviation is, and you've uniquely determined the normal distribution in question. The notation we use is n of mu sigma. This tells you that it's normal. This tells you the mean. This tells you the standard deviation. If you go one deviation from the mean in either direction, 68% of the data is going to fall in there. If you go 2, 95%. And if you go 3, you get 99.7%. Okay? That's a 68, 95, 99.7 rule, which we've done before. It's been an hour. My throat's hurting. Let's take a 5-minute break, and we will continue in 5 minutes. Break. Gray goose. You never have enough gray goose. All right. Yeah. Hopefully everyone's back. It is 5:05. So we just did the 68, 95, 99.7 rule. And we did a number of examples. We also talked about standardizing, which is an extremely important way of comparing two different normal curves by converting them both to a normal whose mean is 0 and whose standard deviation is 1. We do that by taking our data point x, whatever our value is, subtracting the mean, and dividing by sigma. When you do that, you compute what's called the z-score. And the z-score tells you how many standard deviations you are away from the mean. So a positive z-score, you're to the right of the mean. A negative z-score, you're to the left of the mean. And if you have a z-score of 1, for example, you're exactly 1 deviation above the mean. So without knowing where you actually came from, we can still talk about where you fall on a normal curve because I know your z-score. You're 1 deviation from the mean to the right, or you're here, or you're there, and so on. Then we did lots of examples. The standard normal we talked about, that's n of 0, 1. On Crunch It, which you can use for exams, you calculate the cumulative probability up until a point called the cumulative proportion. X less than or equal to a value. Of course, Crunch It can also do greater than a value, just 1 minus that. You can use tables as well, although you don't have to, between 2 values. So you can do this in multiple ways. The way that this particular slide did it is they calculated this part and this part, added them together, and then, okay, 100% minus that gives me the red. You can do to the left, and then subtract, or to the right, and to the right, and then subtract. There's multiple ways. I don't care. Get the right answer. That's all that matters to me. We did examples. Of course, you can go backwards. Okay, if I tell you that I want to be in the top 10%, what number will get me that? That's also done on Crunch It. We can just do it quickly again because we didn't do this one that often. But I would go to normal and I would go to quantile instead. And I would say I want 90% because this, I guess Crunch It only does to the left. If I want 10% to the right, I want 90% to the left. I could put in the mean and deviation. In our case, they were 504 and 111. And when I calculate it, it tells me that for 646.252223775457, approximately 90% is to the left, i.e. 10% is to the right. Oh, did I just delete it? Oh, no. Hold on a second. I got to get it back. We're on PowerPoint number 3, I believe. Okay. So PowerPoint number 3, we were pretty far down. Oh yeah, I think we're pretty much done with this one because then just lots of examples. Lots of examples, yeah. So that's over 3. Okay, so then we were on to slide 4, comma 5. Regression and correlation. We went a little deeper, the 2 types of variables, categorical versus quantitative. Categorical is categories, but there's 2 types of categories. There's ones that can be ordered, ordinal categories, and ones that are not ordered, nominal categories. Like you can't order eye color. I mean, you can have preferences, but there's not really a natural order to them, like there is for military rank or exam grades or evaluations. And then there's quantitative, which fell into 2 categories, discrete and continuous. Discrete has gaps, 1 key, 2 keys, 3 keys, 1 child, 2 child, 3 children. You can't have 2.5 children. Versus continuous, like heights and weights and stuff, which could be anything in a range. We use spreadsheets to do these things for us because it sucks to do them by hand. And of course, the whole purpose of this chapter, and this chapter and the next chapter, 4 and 5, is to talk about whether or not variables are related. Are height and gender related? Gender and political orientation related? Height and children related? Does one affect the other in a meaningful way? And we do that we first have to decide, when we talk about 2 variables being related, do we think that one implies the other or vice versa? Does how much you sleep impact your grade, or does your grade impact how much you sleep? I'm not saying it's not possible to feel stressed by having bad grades and whatnot, but in general, it goes one direction versus the other. So we have the explanatory variable, the X, the independent or the predictor variable, and then we have the Y variable, which is dependent or the response is the Y variable or the dependent variable. Okay, and then we have some examples. We created a scatter plot, which Crunch It did for us, which displays the relationship between 2 quantitative variables, always quantitative. Explanatories on the x-axis and response on the y-axis, like something like this. And when we evaluate the scatter plots, we first have to decide whether it's linear or curved. And if it is linear, or either way, but in general, if it's linear, is it a positive or negative? And of course, for some curved, it could be both, which is why we don't really talk about these for curved. We really focus more on linear. And if it's very weak, it might not even be there at all. It's just a blob of points. We talk about the strength, how strongly linear it is. Strong, moderate, weak, non-existent, and are there any outliers? So we had some examples, right? Still here, we have a general linear trend. We have a general linear trend here. Then Georgia went from being in the middle of the pack to being kind of outside of it. So as a statistician, you might try to understand why that happens. It's a little outlier. It's very hard to tell by hand because these are actually the same data, just different scales, which is why we have a numerical measure of association called the correlation coefficient, or the Pearson product correlation coefficient thing, which is a very complicated formula. Luckily, Crunchit does it for us anyway, so we don't have to worry about that. It's always between -1 and 1. It has no units. Positive, it goes up. Negative, it goes down. 0, it's like flat or non-existent. Closer to 1 or -1, very strong. Closer to 0, very weak. We actually had this general guideline. 0 to 0.1 is essentially no linear association at all. 0.1 to 0.5, it's weak. 0.5 to 0.8, it's moderate. 0.8 to 1, it's strong. And of course, if it's 1, it's perfect. And then we had some examples. Regression is taking your scatter plot and fitting a line to it in a way that you feel that the line is the best representation of the data. And again, Crunchit can do that for us. The method is called the method of least squares, where you imagine a line and misses some points. So you calculate the residuals, which is a difference between the value and what the line says it should be. You square the residuals, you do it for each point, you square them and you add them all together, you get a number. If a different line gives you a lower number for that, that line is better. You're picking out of all the infinitely many lines, the one that gives you the smallest value for that. How do you go through infinitely many lines? You don't, you let calculus do the work for you. Luckily, Crunchit knows calculus, or whoever programmed it knows calculus, and they've already put in the formula for you, so you don't have to worry about it. You get a best fit line, y hat equals a plus bx, or ax plus b, depending on the a and the b, it makes no difference. Just remember, the number that's next to the x is the slope. And to do that, if you did it by hand, I would need to know the r, sy, and sx. And a is the y-intercept by itself. And to do that, I need to know b, which I've already calculated, and y bar and x bar. Some examples. If you square r, you get r squared, obviously, which is the coefficient of determination. What does the coefficient of determination tell you? It tells you what percent of the variation in y values can be explained by variation in x values. As the x values change, the y values are going to change. But there's another reason why the y values change besides just the x values changing. It's because in real life, you're going to have some variation. So the y values are changing for two different reasons. One, different x values. That I can at least understand. But two, there's also the randomness of nature that have to be taken into account. So r squared tells you what percent of the variation in y can be explained by the variation in x. It's like, okay, there's a relationship between x and y. And I know that relationship. So as x changes, y is going to change. I get that. But there's another reason why y changes, which is randomness, things that I'm not taking into account. And that's the other part. So if r squared is 92%, like it is in this example, 92% of the reason why the y values change is because the x values are changing. The other 8%, things that I'm not considering, or things maybe can't even be considered. The whole point of the best fit line is to be able to predict x values that maybe you don't have a y value for, or even if you do, you want to predict it. Just be careful. Don't go outside the data. Extrapolation, bad. Very bad. Right? Make sure it's linear. Use x to predict y, not vice versa. Don't extrapolate. And most importantly, association does not imply causation. Just because two things are connected does not mean one implies the other. And then they just keep going and being very redundant here about these things. What are some possibilities for an association where there's not a straight up causation? Well, maybe two things are associated because something else causes both. The example that the book used was big feet being associated with better learning ability. And why should there be an association between foot size or shoe size and learning ability? Because They both are caused by age. As you get older, both of these go up, and that's why there's a connection between them. But there's a common, a common reason for both. The worst case scenario is confounding, where yes, X may cause Y, and therefore they're associated, but something else also causes Y. So how do you take data when there's something else out there that's explaining away the reason why you have the response that you do? This is confounding the issue, and as a statistician, you would try to get rid of it if you could. And then there was some nonsense that we kind of skipped because these things were pretty stupid. We talked about a residual plot, which is rather than plotting the actual data points, you plot how far things are from the zero. The difference between the point and the line is your residual. So here the actual value is like 3,300, but this height is more like 500 or 400, and that's why the point is like at 400. What are residuals for? They're basically used to determine whether or not a linearity assumption can be assumed. If there's any pattern amongst the residuals, you should be worried. If it's just a regular blob, then things are okay. An influential observation is one that drastically can affect your calculations. We had an example here, subject number 2. If we include it, we have a positive regression line. And if you exclude it, we have a negative regression line. That's very, very significant, changing from a positive correlation to a negative correlation. So we would call that an influential observation or an outlier, which affects things greatly. If you want to throw in categorical data, you can. You just use different symbols. So I can use red and blue, or boxes and circles, or X's and dots, or something. And that takes us to the end of PowerPoint number 4/5. Are there any questions on anything so far?
Nope.
This is just a lot of review, correct?
Yeah.
Okay. And then there was chapter 8, which we don't have PowerPoints for, but we do have, I have it here on the ebook. So we talked about producing data from sampling. We talked about the difference between the whole population and the sample. And of course, the sample is going to be used to predict things about the population. And you must come up with a sampling design. How are you going to do it? How are you going to take your sample? And we talked about bad samples, like convenience samples, which can be very biased, or voluntary response samples, which can be even more biased. Those are both bad. We talked about simple random samples in SRS, the best kind, where any group of individuals is as equally likely to be chosen as any other one. You can use random digits, or in RNG, to create a simple random sample, either on a computer or with a table. And of course, the idea is to take your sample and to make inferences from the sample about the population, which we're going to learn about throughout the remainder of the course, how to do that. Other sampling designs, we talked about a stratified sample, where you divide up the population into pieces and take a little sample of each. I mentioned a cluster sample, which is divided the population into small pieces and take a bunch of those pieces. And cautions about sample surveys. What are some possibilities? Under coverage, you don't get a representative coverage, so you're undercovering everything, or non-response. People just aren't answering, thereby causing undercoverage. Those are both bad. And the wording effects. I didn't mention this last time. I just saw it in bold. The way you word a question can greatly impact how people answer it. Here are some examples. It says, let's look at 8.9. Ask a sample of college students these 2 questions. How happy are you with your life in general? And then how many dates did you have last month? So when asked in this order, it appears that dating and happiness are not associated. But if you reverse the order, how many dates did you have last month? 0. How happy are you? Well, life kind of sucks right now, right? The answer to the first question kind of impacts the answer to the second. Or, oh, I had 19,000 dates this month. It's amazing. So, you know, the way you word it or the way you order the questions can have an effect, which is why you can have entire courses on survey sampling. And just be very careful about that. And then impact of technology, we just mentioned this in passing. It was like 1 page. Just the fact that, you know, with technology, things change, and I don't even know what they're talking about here because I'm just too tired to read it, but you should read it. Anyways, that's it for the first review and clarification. For which one? I don't understand what you're saying. That was 4 minutes ago, but I don't know what I was referring to. Can you clarify what you want me to review when you said review and clarify? You got to sleep. I know. I got to sleep. I know. I know. I know. I got to do a lot of things, but I don't have time, and I'm always behind. Oh, I already did. Good. Okay. So next time, which is class number 11, we will start on the next chapter on Tuesday. But remember that your time is only a small construct of life. I am too tired to even know what that means, but it sounds so deep. I don't know what that is. You gotta open your third eye. Yeah. Okay. Anyways, I have one more class tonight, and then I have a couple hours of tutoring afterwards. So I'm going to let you guys out a little bit early. And did we talk about having a second quiz? Have we mentioned that in passing?
Yeah,
You said you were going to skip it.
yeah.
I said that? Oh, okay, we'll skip it then. Good. I don't have to grade it then, which is good. Okay, so we'll skip it and we'll have some more quizzes later. But for now, remember the test is next weekend, and we will start
Wait, next weekend or this weekend?
next weekend. I would next weekend. I said, right?
Okay.
You guys want to have it this weekend?
No.
Get it out of the way. What do you guys want?
Nah, next weekend.
Next weekend. Okay, next weekend it is. All right, but we will though continue learning new things on Tuesday. We can't just like take a week off or something like that. That doesn't work. So be prepared to learn new material, but we will have the test next week. Okay. All right. So go, leave me alone. I will see you guys next week.
Thank you.